Right, we've been talking about the Gaussian. We've been talking about the binomial distribution, and I'm just going to remind you of what it looks like using R. So let's just have a look at this. Let's fire up R. Here it is. And what I'm going to do is I'm going to consider P equals, let's say, 1/3, and N equals, let's say, 200. So I'm going to consider large N and moderate P, and we'll see what happens to it. You'll be familiar with this from 715184, but it doesn't hurt to go through it again. So what I'm going to use is d binom 0 through, what is it, 200 did I say? 1/3. And they're all my probabilities. So rather than just trying to understand all this drivel, I'm just going to plot it. Naught to 200, because I can't possibly get any more than 200 successes. And with probability of success 1/3, we've covered this, but we expect 200 over 3, or 200 times 1/3, which is 66 2/3, which is of course about here. So what I'm going to do is zoom in on just this area here, because most of the plot is wasted because it's so far down to 0, and we'll start there. What's that? 40 up to 100. Let's try that. You see, all I've done is change the range I'm considering from 0 through, that's the full range there, 0 to 200, 40 to 100. And this is the density of the binomial distribution. It's distorted the horizontal axis a little bit, and I'll just change that now. Now, what I'm going to do is plot the horizontal axis here is just 1, 2, 3, 4 up to 61. Now I'm going to make the horizontal axis 40 to 100. It won't change the form of the diagram. All it's done is change the axis here. So again, we can see this nice figure. So most of the time you get about 66 or 67 successes. But of course, random variability starts kicking in, and you've got up to below 50 isn't completely impossible, and up to 80. So you've got this range that you might observe. And indeed, we can see this by R binom. So we can see in these random numbers here, which have got a range from about 56, is that the smallest one, up to about 70. That's the biggest one, is it? Let's do that again. The motto here is always get R to do the work for you. If I just sort them, I can straight away see the smallest and the largest. And you can see the smallest is 61, which is about there, and the largest here is 80, which is about there. So it's kind of checking out. Right. Well, that's nice. I'm going to give you something which I still regard as something quite astonishing, which is to approximate this curve here with our old friend the Gaussian distribution, which I'm going to spend a good hour, or half an hour at least, talking about. So let me define my terms here. What I'm going to do is talk about the Gaussian approximation, or Gaussian distribution, and then I'm going to show you that the binomial distribution is approximately Gaussian for large n. So, the Gaussian distribution, what is it? Gaussian distribution okay, it's a bell-shaped curve, a probability curve. That looks like this. There it is. And I'm going to give you the distribution for it. And first of all, I'm just going to remind you what this probability curve is. It's formally called a probability density function. Okay, or a PDF. That's how I call it, a probability density function. Shaded area probability that a random variable lies between x and y. Okay, so we can see that this area here is, well, that's what it is. But if I were to work out the probability between these two values here, it would be smaller. Between, let's call it A and B. The probability that your random variable lies between A and B is smaller for two reasons. Firstly, A and B are closer together, and secondly, the height of the curve is smaller as well. So the height of the curve tells you where your probability is concentrated, and of course, the probability is concentrated here, right at the centre. Just to say it's a Gaussian distribution isn't really enough. You need to be a bit more specific. Because I can take this nice bell-shaped curve here, and I can distort it in various ways that mean it stays as a Gaussian curve but looks different. So for example, I can move it to the left if I want. I can move it all the way to the left if I want. Or I can move it to the right. They're still Gaussian. All these are Gaussian. But with different means. There, or there, or there, or there. So we can slide our Gaussian across from left to right. And as you can see here, here's a nice representation of it. We've slided it to 66 2/3 for the mean value here, because that was the mean number of successes in our binomial distribution, indeed. I've got another degree of freedom as well, which is best drawn first, and then I'll show you what it looks like on R. We can also do this. We can get our Gaussian distribution here, and I can flatten it out. Or I can, I've gone off the top there. So this is Gaussian, Gaussian. They're all Gaussian. That one's the other one, isn't it, yeah? All these are Gaussian, but with different widths, and I'll define that in a minute. Widths in scare quotes, because I'm not defining it properly. So we've got 2 degrees of freedom. We can move it left and right, and we can make it sharper and more concentrated like this curve here, this tall one, or we can splurge it out like that. So we've got 2 degrees of freedom. We've got a mean, and also a thing called standard deviation, which equals the width. When you see the formula, you'll see why we can't just talk about the width, because you can see how wide you take it. It's infinitely wide. Sometimes we talk about the variance equals the standard deviation squared. All right? And sometimes you'll write sigma squared equals the variance, and sigma equals the standard deviation. Okay. The Gaussian distribution, as I'm sure you know, crops up over and over and over again. It's the single distribution that's the most useful one, because it describes experimental error extremely well. If you're doing any kind of experiment, whether it's timing something or weighing something or measuring something, it doesn't matter what you're doing, There's always an error, you can never measure it perfectly. That error is always very well described, or not always, but very often accurately described by a Gaussian distribution. So, for example, it's symmetrical between overprediction and underprediction. For example, you can tell that if you've got a width here, occasionally you get outliers, but you can quantify it quite accurately. So let me give you the probability density function for the Gaussian. I'm just going to write it out. Actually, I'm not. What I'm going to do is talk about the standard Gaussian. That's got mean equals 0 and standard deviation equals 1. That's the simplest case. Simplest. You might ask why the standard deviation isn't 0, but if the standard deviation was 0, it would correspond to a no uncertainty case. So it's got to be a non-zero standard deviation, so you make it 1, simply because it's easy to scale by. And that's called the standard Gaussian. And we can plot this in a couple of ways. I'll give you the probability density function for the standard Gaussian. Equals this, 1 over root 2 pi e to the minus x squared over 2. Quite a lot of work in there. Now I'm just going to assert this. I could prove it if I wanted, but I'm just going to leave that there. Quite a lot of work in that, quite a lot to unpack there, so I'm just going to spend a little bit of time talking about that. Where's my black pen? 1 over root 2 pi e to the minus x squared over 2. I'm just going to unpick this a little bit for you. It's e to the minus x squared over 2 times 1 over root 2 pi. This thing here got no x in it. It's just a number. It's just a number. We can work it out. I can use r to work it out for you. 1 over the square root of 2 times pi. 0.398, about 0.4. Where are we? About 0.4. So that's just a number. This bit's got x in it. This has an x. This bit does the work. So as you vary x about, as you move along this horizontal axis here, this bit stays the same because it's just a number, but this guy does the work. I think it's pretty clear that whatever x is, if x, whatever x is, then x squared over 2 is always greater than or equal to 0, isn't it? Yeah? And of course, x squared over 2 equals 0 only if x equals 0. Okay? So we've got e to the minus something positive. Because we've got e to the negative x squared over 2, and this thing here is always positive, whatever x is. If x is negative, minus times the minus is a plus. So we know that e to the minus x squared over 2 is always going to be less than 1, or less than or equal to 1, because e to the power 0 equals 1. Are you guys happy with e to the power 0 equals 1? Yeah? So if you have e to the power negative something, it's going to be less than 1 because it's 1 over e to the power that. So it's going to be equal to 1. So this thing here has got this whole function here has got a maximum at x equals 0. All right? So that's, call it g of x equals that. And g of x has a maximum at x equals 0. And also you can tell just by looking at it that d of x, Gaussian function of x, equals g of minus x. Because if I plug minus x squared minus x into here, by the time I've squared it and divided by 2, I'm back to where I was before. So it's symmetric about 0. It's not about 0 here, but it's symmetric. There's one other feature that we need, and that's the total area under the curve. Now again, this is not a mathematics course, But I might have just written down this, e to the minus x squared over 2. This is no good as a PDF because the area under the curve is not equal to 1. When you're drawing a probability density function, you're representing your uncertainty. You know your variable is going to be somewhere, so the total area has got to be equal to 1. And if I were to choose this curve here, just e to the minus x squared, the area wouldn't be equal to 1. And so it wouldn't work as a probability distribution. So this is why I need to go 1 over root 2 pi, e to the minus x squared over 2. That's okay because the area under the curve equals 1. And if the area equals 1, then it does its job. We've still got no real idea how it works because we don't really understand, or certainly not, I've not explained, how quickly this approaches 0. We can see it's got a maximum at 0 and it falls off, but how quickly does it work? Well, at this point we need to resort to R. So I'm just going to say x becomes, now you've seen this notation, oops. You've seen this notation with the colon from minus 3 to 3, but it's in integers. So I need something a little bit more sophisticated than that, because what I want to do is to have a nice fine plot. Let's say 50. Just a new piece. I'll just do that again. So what I'm going to say is now sec is a sequence from minus 3 to plus 3 and 50 long. So that's the first one at minus 3, like it says. Up, 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 small, bigger, 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 through 0. Where's 0? That's the last negative one, isn't it? Oh, that's negative. Negative. Oh, look, it's minus 0.06. There it is. And then right there it is, yeah. So, and it goes up to 3 and it's 50 long. So what I can do is plot x, comma, and then just whack this distribution function in here. 1 over root 2 pi e to the minus x squared. Let's just do it. I'm going to rephrase it slightly. Exponential function of minus x squared over square root of 2 times pi. So I've got my x, which is my horizontal axis, which goes from minus 3 to 3, and we'll see that that's about right in a minute. E to the minus x squared from there, over root 2 pi from there. Let's just have a look at that. Bonk. It's just the same shape as the binomial distribution, and I'll talk about that in a few minutes. It's got a peak at x equals 0, just like I said. It's symmetrical about x equals 0, just as I said. What's not quite obvious is the width of the distribution here, because it keeps on going forever and ever and ever. I can put x equals anything I like in here. It'll never get to 0. Just gets smaller and smaller and smaller. It never gets to 0. X could be a billion. I'd have e to the minus something big. But it wouldn't be 0. Dividing by that as well. So the width is problematic, but I'm going to define the width as being equal to 1. Now let's just have a look at this formula here. What I want to do is to do the first degree of freedom that we talked about, which was to slide that distribution left and right. I've got my nice distribution, and I want to slide it left and right. Sometimes it's easier to think about moving the curve. Sometimes it's easier to think about moving the x-axis. All I'm really doing when I'm moving this curve about is relabeling the x-axis. Remember it looked the same when I plotted it? So let's just see what that looks like. Let me just write that out again. All I'm doing here is subtracting off a value called mu, which is the mean of the distribution. And in this formula here, instead of writing x, I'm going to write x minus mu. there for x minus the mean. So now, instead of this one being symmetrical about 0, you should be able to see that this curve is symmetrical about x equals mu. So what that corresponds to is moving my, either moving my axis about or moving the curve about. Depends how you think about it. So I'll just do that. Let's say x minus 1. And it moves to the right. Did you see that? Do that again. That's the original curve. Hit the up arrow a couple of times. Now that corresponds to a mean of 1. And you can see here that it corresponds to a mean of 1. I can keep both curves if I instead of plot points. When you go plot, it creates new axes and starts again from scratch. But if I say points, it keeps both points on there, and we can see it's exactly the same. It's just moved left, or I've moved the axis to the I've moved the curve or moved it. Who cares? It's the same thing. And I can move it even further than that. But of course, I've been a bit too clever here because it's gone off the edge. But you can see that it would be there if I didn't. There it is. Gaussian curve. So we can move it left and right. Now you'll remember the other degree of freedom which I've got is to make it more or less concentrated, or to make it wider and narrower. So we'll have a look at that now. There's my standard curve. You'll notice that when I make it wider, it's supposed to be at the same value there, or narrower. You'll see that the height of that curve is changing as well. The height has to change. When I move from the red to the green curve there, it gets wider. I've still got to maintain a total area of 1. And so because it's wider, it's got to squash down. And here, when I go from black to red, I'm bringing it in, so I'm losing area on these regions here. So it's like squeezing a spot. It's going blip and pops out there. Which is an indication, which we'll come back to again and again and again, that the standard deviation, the width of the distribution, is a little bit harder to deal with than the mean. And we'll see that again and again and again because the equations are much more complicated. So how do we do this? Well, last time we said x goes to x minus mu. Now, we're going to say x goes to x minus mu over sigma. This is a scaling of x by sigma. This is sort of a Greek letter. I'm not sure exactly how to pronounce it. I think it's like an S, but I don't really know. So all we're doing is scaling our x. First of all, we can move it left and right, and now we can divide it by sigma. So we can change the width simply by dividing the offset by sigma. So what does that do to this equation here? Well, we've got this curve here, which goes to 1 over 2 root 2 pi. This is not complete yet. I'm going to have to add things to it. E to the minus x minus mu squared over 2 sigma squared. It's sigma squared because we've got a squared here, and there's just a single power here. So that's why it turns to e to the minus squared. But this is no good because the area is not equal to 1. All I've done is simple-headedly take the transformation, here it is, this transformation here. And when I do that transformation, the areas don't match up. So I'm in trouble because all of this distribution here, at x equals mu, it's always got the same value, whatever sigma is. So that sucks because your area isn't quite right. So I'll show you how to correct that now. We haven't incorporated the Jacobian, is the standard way of doing it.